in fact, this another way to think about this S mu's is that there's a torus action on the affine Grassmannian coming from the maximal torus of G check. These S mu's are just these fixed points of this torus action are these points T mu, and this S mu is the attracting set of T mu for a choice of C star for this torus action. Okay, so this is fine, but I'm going to do something. I'm going to try to look at this locus, this Gur lambda bar intersect S mu, in a slightly different way now. For that, I'm going to introduce affine Grassmannian slices. So I take this group, which is, I take G check over polynomials in T inverse, and I take its first congruent subgroup, which means the kernel of the evaluation map when T inverse is 0. So this is a group which is complementary to the group I had before, which was G check over power series in T. So this is sort of strictly in the negative polynomials in T inverse. So it's a complementary subgroup to that G check of power series, and its orbits are complementary to the orbits of G check of power series. They're in fact, they're transverse to each other. And these guys, these orbits here, these W mu's are finite codimension in the affine Grassmannian, unlike the other guys which are finite dimensional. And now I intersect these pairs of transverse orbits. So I take this Gur lambda bar and intersect it with this slice W mu. Okay. So this is analogous in the finite dimensional Flag variety to intersecting Schubert variety with an opposite Schubert cell. So this guy is kind of like a Schubert variety. This guy's kind of like an opposite Schubert cell. Okay. So the theorem is that this W lambda mu has a natural Poisson structure. Moreover, that this set, it contains this Gur lambda bar intersect S mu, and it contains it as a Lagrangian subvariety. Even more precisely, it's the attracting set, as I've sort of explained before, it's the attracting set for a Hamiltonian C star action. So we're in a very nice setup. We have a nice Poisson variety, and it contains this guy we're interested in as a Lagrangian subvariety. So why do we like this? Well, one reason why we like this geometry that we see now is because of this philosophy, I guess, due to Braden, Licata, Proudfoot, and Webster. So if we have a Poisson variety, more specifically, if we have a conical symplectic singularity, and this guy actually is a conical symplectic singularity, this W lambda mu, with a Hamiltonian C star action, and this X, in this setting, X plus denotes that this X has a unique fixed point for this Hamiltonian C star action, and X plus denotes the attracting set of that fixed point. Just like in our situation, X plus X would be this W lambda mu, and X plus would be this Gur lambda bar intersect S mu, which is kind of the guy we're ultimately interested in. I should mention that this guy is a variety, but it's reducible, has many irreducible components called Merkovich-Valonin cycles, and so they're responsible for the weight multiplicity inside that representation. Okay, so following this breakout of Proudfoot-Webster philosophy, we would like to categorify this X plus, which in our case will be this Gur lambda bar intersect S mu. So what does it mean? Well, first, or what's the idea? First, we find a deformation quantization of X. That means we find a filtered algebra whose associated graded is isomorphic to the coordinate ring of X as a Poisson algebra. So this algebra A will be a non-commutative algebra. Its first order commutator will be given by the Poisson structure on the coordinate ring of X. So this is making this an isomorphism of Poisson algebras, commutative Poisson algebras. Second point in this philosophy is that the C star action on X, so X has a C star action, this Hamiltonian C star action, this gives rise to a grading on our algebra A. And in particular, there's now a positively graded part and a negatively graded part. And then we can study a category O for this algebra A with respect to this grading. That means we look at modules for algebra A such that the positive part acts locally nilpotently on the module. So this is inspired, of course, by the example where X is the nilpotent cone and A is the universal enveloping algebra of G modulo central ideal, modulo the maximal ideal of the center. And in that case, this is just this kind of usual category O of a semi-simple Lie algebra, or a block of that category O, I suppose. Okay. So in this circumstance, if we can define a cycle map from the growth in the group of this category O to this top homology of X plus, so this H of X plus, just a short form for H top of X plus. How does the cycle map go? Well, you take your module, you choose a filtration compatible with this filtration on A, you take its associated graded, so now it becomes a module over the coordinate ring of X, and because the positive degree stuff in A acts locally and nilpotently on the module, when I take the associated graded, that stuff will also act locally and nilpotently, and that means that this associated graded guy is supported in X plus, and that defines this cycle map. So this cycle map's like not typically an isomorphism. More often to find an isomorphism, you would work with some resolution of X and enhance A to a sheaf of algebras on the resolution, and then take a cycle map there. But anyway, for my purposes for today's talk, let's just speak about this more naive construction. Okay. So this map typically will not be a resolution, but nonetheless, we can still, this map typically will not be an isomorphism, but nonetheless, we can still motivates us to think about the left-hand side. Okay, so we'd like to carry out this program for our truncated shifted Yangians. So to do that, we need to do the first step. So X will be our affine Grassmannian slice. Sorry, I meant carry out this program for the affine Grassmannian slice. So X will be the affine Grassmannian slice, so we need to find an algebra A whose associated graded is isomorphic to this algebra, to this coordinate ring of X. And so in a series of papers with Tingley, Webster, Weeks, and Jacobi, we studied these algebras, and we called them truncated shifted Yangians. And they are defined as actually subquotients of the Yangian. So I'm not going to get into the definition for today's talk. Well, maybe a little later we'll see a sort of definition of them, but not by generators and relations. But they do have a definition by generators and relations, and can be worked with algebraically quite effectively. So those are these algebras, YLM-nu. So YLM-nu is this algebra whose associated graded is the coordinate ring of this affine Grassmannian slice. And then following this philosophy, its category O should be viewed as a categorification of the top homology of this attracting locus, which, as I mentioned before, by the theorem of Mirkovich and Belonin, is the weight space in the representation. So it's natural to have some kind of theorem like this. What does a theorem mean? So this is kind of just a heuristic statement of the theorem, not a very precise statement. But what it means is that that we have an action of our categorical action of the Lie algebra G. So Chevrolet generators of our Lie algebras, EIs and FIs, will act as functors on this category, moving you between category O's for different y lambda mu's. And moreover, this cycle map will give us a map from the Grothney group of this category O to V lambda. And that map won't be an isomorphism really, usually. Actually, this Grothney group will be something more like a tensor product representation rather than the irreducible representation. So there's a slight discrepancy here. But to be a little bit more precise, these algebras actually come with some parameters analogous to the central parameters in earlier when I was speaking about central quotients of universal enveloping algebra, semi-simple Lie algebra. These algebras here come with some central parameters and come with some parameters, and the representation you get depends on the choice of those parameters. So for certain special choice of the parameters, you actually do get exactly V lambda. For other kind of generic choice of the parameters, you get tensor product of sort of fundamentals corresponding. Okay, and maybe one other thing before I move on is that these truncated shifted Yangians, there's some natural examples that you already know about. For example, the universally enveloping algebra of SLN, modulo again a central ideal, is an example of such a truncated shifted Yangian. And more generally, finite type A W algebras are examples of these truncated shifted Yangians. Okay. Any questions? Okay, so I'll explain now a little bit the idea behind how we prove this theorem. So the main goal today is to, well, explain a little bit about the idea behind this proof of this theorem, and also explain what is this categorical G action on the left side. So there should be some way of relating these different categories of modules. These should be some functors, EI and FI, but a priori it's not very clear what those functors are. Because somehow one reason is because of the geometric Satake correspondence is sort of very indirect, so it's not a priori clear what the functors are. Okay. I'm just checking to see, is there any questions? I can't somehow see the chat or anything when I'm in the, okay. I can't, okay. I'll go back here. Is everyone still with me? Can you still see the screen? Okay, so let's suppose we have a complex reductive. Oh, so now I'm going to change the. Okay, so ultimately, one of the main ideas behind this proof of this theorem is to use what's called the theory of Coulomb branches, as developed by Braverman-Finkelberg-Nakajima. So that's what I'm going to explain now. Okay, so now so now we're changing gears. So suppose now I have a complex reductive group G, which is like unrelated to the group I started with before. So in our situation, this G will actually end up being a product of GLs. And V, a representation of this group. Again, unrelated to this V lambda that I started the talk with. So from this data of G and V, physicists can define a 3D supersymmetric gauge theory. And they define two spaces. One space they call the Higgs branch. And the Higgs branch has a relatively straightforward mathematical definition. We form the cotangent bundle of V and take the Hamiltonian reduction by the action of G. So this cotangent bundle of V has a moment map, well, denote mu, and we take the zero level of that moment map and then divide out by the action of G. We could take here a projective DIT quotient or affine DIT quotient. We have some choice, but in any case, this gives us what's called Higgs branch. And then a more mysterious space, which a physicist called the Coulomb branch, and which mathematicians, as I mentioned now, have been studying for the past 5 years, following the work of Braverman-Finkelberg-Nakajima. And I'm going to tell you its definition, but let me just tell you a very rough definition first. So very roughly, oops, I realized there's a typo here. Sorry, this point should actually say P1. Very roughly, you take the space of all maps from P1 into the stack V mod G and take the homology of that space of maps. And that is endowed with a convolution algebra structure, and then you take spec of that algebra. Okay, let's see an example. So here's an example. If we take G to be C star and V to be Cn, well, Higgs branch is just C2n minus action of C star, and it turns out to be space of square zero matrices of rank at most 1. So this T star of Cn is like a vector and a covector, and together they give you this matrix. This rank is at most 1. On the other hand, the Coulomb branch, for reasons which are initially maybe mysterious, is just C2 mod the Z mod n. So this Kleinian singularity C2 mod Z mod n in this case. In n is 2, these two things happen to coincide. Okay, now I'd like to give a more precise definition of this Coulomb branch. due to Braverman-Finkelberg-Nakajima. And the definition also involves the affine Grassmannian, but again, kind of unrelated to the affine Grassmannian I was talking about earlier. So I'll introduce notation. I'll use K for Laurent series, O for power series, and I take the affine Grassmannian, again, G of K by G of O. And I'm going to now form a vector bundle, infinite rank vector bundle over the affine Grassmannian, whose fiber is isomorphic to V tensor O. So it's pairs consisting of a point in affine Grassmannian and a vector in V tensor K, such that the vector lives in this G translated V tensor O. Another way to think about it is affine Grassmannian, as it's kind of well known when G is GLN, it's sort of a space of lattices. And in general, if you're given a representation of G and a point in the affine Grassmannian, you get a lattice in V, namely this lattice, G acting on V tensor O, an O lattice in V tensor K. And so this just is like the vector bundle over the affine Grassmannian, where over each point you put that O lattice in V tensor K. So it's, in the GLN case, it's a sort of tautological kind of vector bundle. And now I do an analog of a Steinberg variety kind of construction. So I take two copies of this vector bundle, and I take their fiber product over, not over the affine Grassmannian, but over the other thing they map to, which is V tensor K. So I end up with this space Z ends up being triples, two points in the affine Grassmannian and one vector, which is in the lattice common to both affine Grassmannian points. And then I can form, so this is Steinberg variety, and it has a natural kind of geometric interpretation, where more precisely it's stack quotient by the action of G of K has a natural moduli space interpretation. That's pairs consisting of a principal bundle and a section, but on a funny space. So it's a principal bundle and a section, but not on some normal looking space, but on this weird curve, which I call a ravioli curve, which is made by gluing two copies of the formal disk together over the punctured disk. So it's a non-separated curve. It contains two origins and looks like a ravioli. So I have so this space ZGV mod G of K is the moduli space of such pairs of a principal G bundle and a section over that space. And then, so the construction of Braverman-Finkelberg-Nakajima is that we take the homology of that moduli space, so G of K equivalent homology of ZGV, and this space is endowed with a convolution algebra structure analogous to the convolution algebra structure on the homology of the usual Steinberg variety. But maybe an interesting feature is that it turns out to be a commutative algebra. And another interesting feature is that it admits a non-commutative deformation. So we can turn on an additional action of C star. This C star acts by rotating the loop. So it acts on the variable t, multiplication by some scalar onto the variable t, or in this geometric interpretation, it acts by acting on those disks. And so we use that, turn on that C star, and then we have a parameter h bar, which is the C star covariant parameter, and this becomes a non-commutative deformation of this algebra. In a slightly different sense than I said before, it's like if we were to set this h bar to 1, then we would get something whose associated graded with this. Here I'm saying that it's a h bar kind of quantization, so formal quantization rather than filtered quantization. And then this spec of this algebra AGV is called the Coulomb branch, and this non-commutative version is Coulomb branch algebra. So it's an affine variety or affine scheme, and it comes with a canonical sort of deformation, this AGV, HGV. Are there any questions? Are you still there? Can someone just say something so I know you're still listening?
Yes, we are. I mean, at least I am here.
Great.
I'm still here as well.
Great. Any questions? Okay. So in this Google Meet, you don't like see any, when I'm doing this full screen, I can't like see anything about people watching or anything, unlike in Zoom. Anyway, otherwise it seems to be fine. Okay, so so this is the definition of Braverman-Finkelberg-Nakajima. So this is relevant to our story because of the case of Quiver gauge theories. So what does that mean? So let's start with lambda and mu as before. So lambda is a dominant weight, mu is just a weight, and mu is less than lambda. And remember, this mu less than lambda means that I can write lambda minus mu as a sum of positive roots, or as linear combination of simple roots with coefficients being non-negative integers. And similarly, I write lambda as a linear combination of the fundamental weights. So this lambda and mu are, again, the weights of the group we sort of started with, not this group G that appeared in the previous slide. Now we form the kind of construction we would do if we were making a Nakajima quiver variety. So we first of all fix an orientation. So that's what I mean by Dinkin quiver. We fix an orientation on our Dinkin diagram. And for each edge in that orientation, we put this HOM C to VI Vj. So we put vector spaces of dimension Vi on those vertices. And then we put framing vector spaces C to the Wi. And we also take this HOM from VIs to the Ws. So a familiar construction from the theory of Nakajima quiver varieties. As I mentioned, if you then double it and then take say projective GIT quotient by the action of this gauge group, which is the product of GLVIs, you'll get the Nakajima quiver variety. So this is my V and this is my G. And if I, instead of doing this, so this is what's called Higgs branch. So the Nakajima quiver variety is the Higgs branch. If you remember the recipe for the Higgs branch, it was this. Now I'm going to do Coulomb branch. So instead of doing this, I can do this much more complicated thing involving looking at the affine Grassmannian of G and this vector bundle and so on, forming this funny algebra A. Then theorem of Braverman-Finkelberg-Nakajima with the second part proven also, I mean, in an appendix where there was more authors. So is the following. First of all, we have the assumption that mu is dominant. So in what's here, I never used, I mean, in definition here, I don't use that mu is a dominant weight. Mu could be any weight. But for my W lambda mu at the beginning of the talk, for it to have good properties, I needed the mu to be dominant. So here, for this theorem, I assume mu is dominant. And I obtain that the Coulomb branch, so spec of this algebra, is the W lambda mu I start with, this affine Grassmannian slice. So again, it's pretty remarkable that the affine Grassmannian slice, something kind of, I don't know, geometric, has a nice interpretation in geometric Satake and so on, and it comes from this construction which started with the same data that produced the Nakajima quiver variety. And the second point is, well, closely related to the first point, is this algebra you get this way is this truncated shifted Yangian, the non-commutative algebra. Okay. So one nice thing about the theorem is that, well, the theorem is just true when mu is dominant, but if you ignore this assumption that mu is dominant, you can use the left-hand sides to give a definition of the right-hand sides. So one sort of obstruction to the theorem that I mentioned a while ago, that a main theorem about this categorification, is that you need to have these weight spaces even when mu is not dominant, of course, to make a representation. But naturally, this W lambda mu's only kind of work when mu is dominant. So this theorem gives you a way to define them when mu is not dominant. And then they're called generalized affine Grassmannian slices. So again, using these Coulomb branches, we can now generalize definition of these affine Grassmannian slice and the truncated shifted Yangians to the non-dominant mu. And in fact, surprisingly, they have a sort of geometric description too, but it's maybe not one you might, at least no one I don't think kind of guessed this geometric description exactly before thinking about Coulomb branches. And the geometric definition is that it's actually not a subvariety of the affine Grassmannian anymore, but just the subvariety of G check of K. Anyway, the definition's here, and it's, well, I won't try to explain it because it's not maybe super enlightening. And another thing is this Y lambda mu. So that was defined as this called truncated shifted Yangian, was defined as a subquotient of the Yangian in the dominant case. And now in the case when mu is not dominant, it's not a subquotient of the Yangian, but it sort of has a pretty similar generators relations description. And that we sort of did already have guessed before the thinking about it as a Coulomb branch, but still having the Coulomb branch description of it makes it much more tractable. And now I'll mention the theorem of Krylov about this W lambda mu. So remember, one of the reasons why we were interested in W lambda mu in the first place is because it contained this locus, this Mirkovich-Volonin locus, as a Lagrangian attracting set. And one amazing thing is that even when mu is not dominant, and we use this funny definition of W lambda mu, like this one, or the one as a Coulomb branch, it still contains Gur lambda bar intersect S mu as a Lagrangian attracting set. So that's an indication that it's definitely the right object to look at. Okay, so now I can remind you that our core theorem was that this direct sum of this mu's of y lambda mu mod category O's categorified V lambda or some tensor product representation or some other representation. And so in order to establish this theorem, our proof was to relate the left-hand side, these category O's, to modules for so-called KLR algebras. Should say modules for KLR algebras. Okay, and so I don't want to get so much into the details of these KLR algebras because it's like a whole big topic, but just in case there's people in the audience who are already experts in these KLR algebras, or I call them KLRW algebras. W stands for Webster, or some people call them Webster tensor product algebras. So I consider these algebras where we have Wi, red strands labeled I. So remember Wi was determined by this lambda. And Vi, black strands labeled I. So remember Vi is determined by like lambda minus mu. And then I consider this usual kind of cyclotomic kind of quotient where I quotient by the diagrams where the leftmost strand is black. And then from Webster's work, modules for these algebras categorize these weight spaces in V lambda, or more generally, their tensor products. And so the theorem we proved in order to establish the theorem at the top of the page is that the modules, that this category O is actually equivalent to modules for these KLRW algebras. And the proof is pretty algebraic, just involves like working with these algebras and so on, but it kind of uses their sort of description as Coulomb branch algebras. Okay, so from this theorem, we get the previous one, namely we have functors from Webster's work, EI functors from T lambda mu mod to T lambda mu plus alpha I mod. And then since we have a vertical equivalences here and here, we get a functors this way, and these functors give us this categorical G action. So that's okay. That was paper we wrote like last year, but it's not completely satisfactory because we would like some way of thinking about these functors which doesn't involve this equivalence. So some way of thinking about these functors which is intrinsic to their nature as being truncated shifted Yangians, or intrinsic to them being Coulomb branch algebras. So that's what I'm going to discuss now. Okay, so if we think about it from the Coulomb branch point of view, we have this pair GV, which comes from a quiver, as I mentioned. G is some product of these GLs, V is this hums, blah, blah. And then we have another GV, which gives us this guy here. How do they differ? Well, what's changed is that I've just changed the ith vertex by 1. So I've reduced what's happening at the ith vertex by 1. So my group G prime has shrunk a little bit. Went from like GLVI to GLVI minus 1 in that spot. The other GL stayed the same. And my V has also changed a bit. It's like there was arrows going, just because that guy's gotten smaller, this V prime has gotten smaller. Okay, so I have to relate some AGV to some other AG prime V prime. So at first glance, hard to see what exactly the general viewpoint of the relationship between G and G prime and V prime is. but that's what I'm going to explain now. Okay, so let's go to an arbitrary pair of a reductive group and a representation again. So I return to the general case of Coulomb branch, general setting of Coulomb branch algebra, so not necessarily Quiver theory. And I'm going to add one more piece of data, which is just a choice of map from C star into G. Okay? I mean, and we may as well assume that this lands inside the maximal torus of G. And let's let L be the centralizer of this image of this C. So it's a Levi subgroup, and P be the corresponding parabolic subgroup. In other words, P is the subgroup whose Lie algebra consists of those non-negative weight spaces for the action of the C star on the Lie algebra of G. Okay. Then we're going to be interested in the Coulomb branch algebra associated to G and V, the non-commutative Coulomb branch algebra associated to G and V, and to the pair L, so this Levi, which is kind of like the invariance in some sense of this C. I mean, it's Lie algebra is the invariance of C acting on G. And the invariance of C acting on the representation. So this C star embeds in G, so it acts on the representation, so I can take the invariance. Okay, equivalently, this is the weight spaces of this representation, which pair with 0 to C. And this VC is indeed a representation of L. So these two algebras are related by a series of 3 steps. First of all, there exists a parabolic version of this Coulomb branch algebra. So these parabolic versions of these Coulomb branch algebras were kind of, I guess, introduced by Webster, and certainly studied a lot by Webster, especially in the case of where this P is a Borel, the kind of Irohoi version. So in this version of the Coulomb branch algebra, you basically just replaced your affine Grassmannian by the corresponding partial affine flag variety corresponding to P. Okay, so it would be in the case, if P was B, it would be the full affine flag variety. If P is G, it would be the affine Grassmannian, and if P is in between, it's a partial affine flag variety. So you do everything you do, the same definition as in as you do for the Coulomb branch algebra, but with that partial affine flag variety, and you end up with actually a Maria equivalent algebra. They just differ by a matrix algebra whose rank is related to the Weil group in this P. Okay. Second point is that there's an inclusion of algebras between the algebra associated with this L and V and this parabolic guy. And the third point is that this algebra associated to L and VC is just a localization of the algebra associated to L and V. So this element C, it can be viewed as defining a point in the affine Grassmannian of G. This G here, of course, because it's a coweight of G, so it gives you a point in the affine Grassmannian of G. And, or in the affine Grassmannian, even better in the affine Grassmannian of the group L. And then you can take its fiber over this point, and that gives you inside this BFN space, and that gives you, you take the homology class of that. So RC is a homology class sort of living over that point in the affine Grassmannian. And then, so that single homology class, that homology class gives you an element in this algebra, and if I invert it, then I get this isomorphism. So altogether, we can use this theorem to define a nice restriction functor. How does it work? Well, we start with a module here, we apply the Morita equivalence, we get a module here, we restrict it under this inclusion, and then we apply localization to get a module for localization. So this altogether gives us a nice restriction functor, whose properties we can study quite well because each of these steps is sort of well controlled. So it gives us a nice restriction functor from this Coulomb branch algebra to that Coulomb branch algebra, and we can prove that it takes modules in category O to modules in category. Okay. So now let's fix lambda and mu as sort of the beginning of the talk, and then we have a corresponding Quiver gauge theory. So again, that means we have G being the product of GLVIs, and we have V being the direct sum of these HOMs corresponding to edges and corresponding to frames. And as I mentioned, now the additional piece of the data is this choice of XC. So what XC will I choose? So first of all, I'm going to single out one of these GLVIs. That's going to be the one where we're going to do this adding the alpha I. So all this is, remember, our motivation is to try to explain this functor from modules for y lambda mu and y lambda mu plus alpha I. So there's a fixed choice of this I involved. So here's where we're going to use that I. So I look at that copy of GLVI sitting in G, and I take my C to be the inclusion of C star into that GLVI, the omega 1 inclusion. That means I just consider the C star mapping into the upper, top, whatever, left corner, top left corner of the matrix. Okay.
Joel, so you have a question on the chat.
Yeah, I suppose I don't have any convenient way of seeing the chat. Okay. I wonder if there's a way to keep both screens open at once. Okay, anyway. In the previous slide, did we assume that the Coulomb branches admitted symplectic resolutions? And so the question was whether we assumed the Coulomb branches admitted symplectic resolutions. No. What? So I haven't talked at all about symplectic resolutions in this talk, maybe just as a word. So sometimes these affine Grassmannian slices admit symplectic resolutions, and sometimes they don't. The main circumstance in which they do is when lambda is the sum of minuscules. But whether or not they admit symplectic resolutions, when they do admit symplectic resolutions, you can construct them using this. There's a modification of this Coulomb branch construction to produce their symplectic resolutions, and or there's a way of doing it using the original definition of these W lambda mu's. But in any case, the symplectic resolutions don't really play much of a story in the talk. I mean, if you want to think about this cycle map that I mentioned, you'd like the cycle map to have a better chance of being an isomorphism, then it's natural to work with sheaves of algebras on the symplectic resolution and sheaves of modules, but it doesn't actually really play a role in the story, and I didn't need it in any moment. That's all. Okay, I go back to my slide. Yeah. Okay, so again, I mentioned, so where were we? We were going to apply this. Oops. Sorry. Okay, we wanted to apply this general setup. In this general setup, we have a G and a V, and then we're going to relate it to a L and a V C. So I know what G and V are, and I know what I want L and V C to be, but a priori I don't obviously know what C is. It's not sort of given to me, but now I'm telling you what to choose for C. So choose it to be this thing. And what's good about it is that what will L become? Well, L will be the centralizer, which means that in this ith piece, you're going to end up with GL1 cross GLVI minus 1. So we've split off this, we split this GLVI into GL1 cross GLVI minus 1. And what will VC be? By taking things which are invariant under the C, you're basically cutting all those arrows which go to this one block. So we sort of split one of the nodes in our quiver into a 1 and a VI minus 1, and then we erased all the arrows going to this one guy. So in that way, this Coulomb branch algebra ends up basically being y lambda mu plus alpha I, except that there's this little GL1 sitting around. So I also get a tensor product with, this is actually the Coulomb branch algebra associated to GL1 in the trivial representation. So if you take GL1, which is C star, with the trivial representation, the corresponding Coulomb branch algebra is the algebra of differential operators on C star. The corresponding Coulomb branch is the cotangent model of C star, and the Coulomb branch algebra is the differential operator C star. But this guy sort of, so it's a kind of Weyl algebra. But anyway, this guy's going to like sort of play not an unimportant role. So from the construction of the previous slide, I said that these two algebras now are related by this nice series of steps: rate equivalence, inclusion of algebras, and localization, which allowed us to define a functor from here to here, which I called a restriction functor. And so kind of the main theorem now is that this gives a Coulomb branch way of thinking about the functors EI that was originally defined using the equivalence with KLRW algebras. So so again, I had wanted to define these functors in a way which was more intrinsic to their nature as Coulomb branch algebras, and using this theorem on the previous slide, this which I call parabolic restriction for Coulomb branch algebras, now we have a way of defining this functors in this way. Okay, that's the end of the talk.
Thank you. So we have Irako, you may talk. I mean, you can switch on the microphone. There is honestly no need. I mean, Irako asked you a question.
Yeah,
he wrote in the chat, but please go ahead and talk. I mean,
yeah, I see. What happens in the non-simply laced case? It's a good question. I guess. Okay, even that question has two parts. You could ask what happens in the symmetrized case, but not necessarily simply laced. And then what happens in the symmetrizable case? So we do have these algebras y lambda mu even in the symmetrizable case. I guess, well, yeah, I guess okay, I'm not very confident now saying what the exact state of knowledge is regarding the non-simply laced case. Obviously, yeah, probably Alex Weeks would be the person to ask, as Hirako knows. But yeah, I don't think I can give a very good answer to that question at the moment.
So which part of the proof you use the assumption, simply laced assumption?
Do you mean in the equivalence with the which well,
so in your proof of the main theorem.
So okay, well, first of all, there's the theorem about the equivalence with the KLRW algebras, and in that theorem, certainly the proof that we have written is only written in the simply laced case. I mean, it's used all the time because the theorem is kind of very algebraic, so we use a explicit algebraic description of the algebras. So so that part is 100% is for sure true, but I mean for sure uses the simply laced case. But the truth is that I think that theorem should generalize without too much difficulty, at least to the symmetrized case. Symmetrizable, I'm less sure. And then in the later part about interpreting the functors in Coulomb branch terms, again, in the symmetrized case, probably everything will go through in the same way. And in the symmetrizable case, I guess we would need to think about your work with Alex about the Coulomb branches in the symmetrizable case. So I haven't thought that much about that.
Yeah, so in our work, so if we go to the quantization, we end up with AD type, and even if we start with BC PCG.
Yeah.
So we're a little confused about it.
Yeah. I think, well, I forgot. Once okay, well, I don't, well, I can talk to Alex, or you can talk to Alex, but I think once Alex explained to me how we can think about that in the, as related to these KLRW algebras. There's some manifestation of that we can see, but I'm not sure how it's supposed to work.
Thank you. Thank you.
Any other question or remark?
I have a question. Joel, what portion of the talk works for k-theoretic case?
That's an interesting question. I don't think much of it worked. I mean, so in the k-theoretic case, instead of these affine Grassmannian slices, you get slices in the affine flag variety. Instead of this truncated shifted Yangians, you get these truncated shifted quantum affine algebras. So this is all studied in Finkelberg-Nakajima. So certainly that part works, but the part about the categorification and the equivalence with the KLRW algebras, I have no idea. Probably it doesn't work, but I have no idea really. And the part at the end about the relations where you when you introduce this coweight and you consider this parabolic restriction stuff, that part is kind of general, so I would expect that part will work fine in the general result there about the read equivalences and the localization and so on. That part should work fine in the k-theoretic case because it's kind of it's kind of general and basically just uses the geometry, so it should go through fine. That part should go through fine. But whether in this Quiver case it would give you something like a categorification, I couldn't say.
And so thanks. And is it possible to say in 2 words what's the idea kind of proving that Morita equivalence between the Coulomb bridge and its parabolic version?
Yeah, I think it just not very complicated. Just because the spaces involved is a kind of one space is a kind of bundle, flag variety bundle over the other, and then the equivariance of the group also changes. So you end up with something like P equivariant cohomology of G mod P, and then from that you get it.
Thanks.
Any other question or comment? Okay, let's thank Joel again.
I think there's a question, but
there is a question. Okay. Yeah, please go ahead. So let's please.
I think it's Roma, but his microphone is muted, so we cannot hear him. No, we still can't hear him.
We cannot hear you, but your microphone is on.
Rob, yes, your microphone is muted.
It's easier if you write on the chat.
Oh,
now it's fine.
Now it's
fine.
Okay. So sorry. Like, actually, I have maybe a stupid question. So I'm a bit confused. Where do you have like finite W algebra or like real huge W algebra?
The truncated shifted Yang is a finite W algebra. I mean, sometimes it's isomorphic to a finite type A W algebra. It's just a phenomenon which exists only in type A.
So in your talk there was only connection with finite W algebra, right?
Yeah.
And but I thought that in Finkelberg-Zimbaluk was real truncated, real shifted Yangian or shifted toroidal algebra. Okay, maybe.
Not sure either.
Okay, sorry.
Any other question? So then let's thank Joel again.
Right. Bye, everyone.
So, okay, Joel, can you send me the slides?
Yeah.
Okay, thanks. Thank you for giving the talk.
Thanks. Thanks for inviting.